We next introduce a work based on local feature point to do video event detection. And in this work, they not only use the local feature point, they also use motion information and the visual relatedness. This work was published in year 2008 in ACM Multimedia Conference. And the following slides are provided by Professor Jiang Yugang. And Professor Jiang Yugang is right now in Fudan University in Shanghai. And his advisor was the Hong Kong City University of Hong Kong. City University of Hong Kong. Okay, Professor No. Okay, and we also can read a lot of studies, a lot of papers from the Professor No. Okay, and this paper is the video event detection using motion relativity and visual relatedness. Just like the semantic concept detection before, as the track width benchmark involved, more and more semantic concepts are considered in the traffic benchmark, and many of them are actually event-based concept. Okay, and in the traffic benchmark, they may have static concept like person, bridge, flower. So they are a static concept. But there are also many event-based concepts like car moving, people walking, airplane flying, and so on. And in the search task of the traffic 2008, 16 of the 48 queries are related to events. And when we try to detect event-based concept, we need to consider not only the visual appearance, the visual characteristic, but also the motion information, just like this. Okay, and the event-based query like a find shots of person getting out of or getting into a vehicle. To find such video shots, we need to consider not only the static semantic meaning, but also the motion information. Just like this, if we don't consider motion information, so lack of effective features and models for describing moving object will not be able to develop an accurate video event detection module. Like this, what is this? This is the airplane landing or airplane taking off. By viewing a static image, we cannot distinguish these two events. By this static image, is she dancing or is she walking? We don't know. By these static images, is they catching something or they throw something? Okay, sometimes we are not easy to distinguish these two cases if we don't consider motion information. And for existing approach in year 2008, there have already many features proposed to do semantic concept detection, like the keyframe-based feature, like color, like visual word. Okay, and the idea is based on static images, we may extract many features, maybe many local features like shift, and then we do we clustering the keyframe. We cluster the key points to form a visual vocabulary, and the key points belonging to the same cluster are corresponding to the same visual word. So we can represent an image by a distribution of visual word to describe the meaning of an image. And by such approach, they mainly describe what appear in this image. Like people, there may be people, there may be building, like sky or road. So they rely on visual appearance or visual key points to describe the content of the image. There are also some approach rely on motion distribution, like the grid-based motion histogram. Okay, so we can construct a motion histogram to describe how object move in the video. Okay, and basically this approach describe how object move. Okay, the problem of these two approaches are they just consider what and how aspect separately, and they don't jointly consider object's motion. Okay, and they also don't consider the motion relative to the camera motion. Therefore, the motion information may not be very accurate. So in this work, they try to propose an approach jointly consider how object move and what object appear in the video. So they try to consider a sequence of image, and they try to describe both what and how. So one traditional way is they just conduct object detection, they do object tracking, and then recognize. And the approach proposed in this paper is they try to describe the motion of visual words. Visual words describe what appear in an image, and the motion describe how this object move in this video. So they try to jointly consider them. Also, they also try to extract more accurate motion information. So they introduce the idea of motion relativity. So according to the Galileo's principle of relativity, all uniform motion is relative, and there is no absolute and well-defined state of the rest. So they try to eliminate the influence of camera motion, and they try to more accurately describe object motion. So the methodology proposed in this method is actually an evolution along the axis. Okay, so first they try to use back-of visual word to describe video frame. Okay, and then they enhance the BOW approach by consider the motion of visual word. And then they try to more accurately describe motion information. So they propose relative motion, so RMH BOW. And finally, they also try to expand the visual relatedness because some concepts are related. So they try to handle the visual word disambiguation problem. So they try to expand with the visual relatedness. So let's go from the first approach. The first approach is the so-called back-of visual word. So from images, we can extract many shift features, and based on the feature, the key point collection, we can do k-means clustering. Therefore, similar key points may be clustered together, and the key points corresponding to the same cluster are viewed as belonging to the same visual word. Okay, so after k-means clustering, we can construct a visual vocabulary consisting of k visual words. Okay, so given an image, we can extract shift visual points, and then we quantize each visual point into one of the visual word. Okay, depending on the distance between this visual point to others that have been clustered. And then we can describe an image or a video keyframe by a back-of visual word histogram. So in this histogram, that means how many times the visual word number 1 appear, how many times the visual word number 2 appear, and according to the distribution, we can roughly describe the visual characteristic of such image. And this is a very traditional but effective method to describe images in early years, in around early 2000, starting from 2003. The big visual word approach was proposed and was widely adopted in many applications. To enhance the traditional big visual word, they proposed the motion of visual words to jointly consider not only what appear in image, but also how this object move. The idea of motion of big visual word is like this. They try to describe how visual word move. Okay, so the original BOW method is to describe the presence of object. And then the motion on BOW is the motion activity of these objects. Therefore, for each visual word, for each key point that corresponds to one visual word, we track the movement of this visual word. And then we quantize the motion direction into one of the four moving direction. Okay, and then we just calculate the numbers of visual word moving toward the the first direction, and then the numbers of visual word moving toward the second direction, and so on. Therefore, by summating all the key point P corresponding to the visual word A, so the NA is the set of points, and P is one of the point. And then we check the motion direction of this key point P, and then construct and then accumulate the numbers of key point moving to this direction, and then we construct a four-dimensional motion histogram that is called HIA, where I indicate the the moving direction, and the A is the visual word. Okay, so basically we finally can construct for each visual word, we can construct a four-dimensional motion histogram. And this is the absolute motion direction. But if we also consider the camera motion, the object motion may be different. Okay, and then if we want to more accurately describe the motion information, we may need to describe the relative motion rather than the absolute motion. Therefore, they further propose the relative motion histogram of big visual word. The problem of absolute motion is that the motion will be distorted by the camera movement. So the solution would be we need to describe the relative motion rather than absolute motion. Like these two examples, when if there is no camera motion, then for example, these people, there is a visual point on her face, and then the visual point will move toward the right. That would be fine. But if the camera also move, so for a key points P2 here, because when these people walking toward the right, the camera also move to the right. Therefore, the absolute position of this visual word may always keep the same. Therefore, it may not be able to accurately show the motion information. Therefore, they also try to describe the relative motion histogram. Okay, the way is also simple. We consider two sets. The first set is the key point, the set of key point corresponding to visual word A. The another set is the key point corresponding to the visual word B, and the P corresponding to visual word A Q corresponding to visual word B. And right here, we just calculate the relative position between the key point P and the key point Q. And then we quantize them into one of the motion range. Okay, and as you can see here, the physical meaning of this formulation is that we calculate the relative motion between visual word A and the visual word B. Okay, and this is the relative motion histogram, RHI-AB. Okay, so this is the relative motion histogram, and this would be a three-dimensional data structure, because right here we have n visual word, and we have another n visual word, and for any pair of visual word, we will calculate a four-dimensional motion histogram, okay, corresponding to different moving direction. Therefore, it's a three-dimensional data structure. So this is a improved version of the motion histogram of visual word. Okay. They also try to further improve the proposed work by expand the visual relatedness. So what is the idea? The problem is they try to solve the visual word ambiguity problem. So what is this problem? Because right now we have already constructed the visual vocabulary, and the first visual word may corresponding to the car wheel. The second visual word may also corresponding to the car wheel as well, but different car. The third visual word may corresponding to human eyes, and so on. And if we just consider the distance between different visual word histogram, we actually think the distance between V1 and V2 and the distance between V1 and V3 equally. But actually, semantically, V1 and V2 are more similar because they all correspond to car wheel. Okay, the semantic meaning between V1 and V3 should be larger than V1 and V2. So this is the so-called visual ambiguity. These two figures, these two images should be more similar. Therefore, the image, the key points extract from them should be also similar. Okay, so the solution is visual word relatedness. If we can understand, if we can estimate the similarity between different visual words, we will be able to more accurately calculate the distance between different images. So how can we do that? In this work, they propose the visual word ontology. Okay, we have already some predefined textual ontology like WordNet. In WordNet, it defines the hierarchy between different concepts. For example, car and a trunk are all belonging to motor vehicle. Motor vehicle and the table both corresponding to the concept object. Okay, and this textual ontology is defined manually, and this has been widely applied in many applications. And in this work, they try to automatically construct a visual ontology that is similar to WordNet. So how do they do that? Basically, they do this based on agglomerative clustering. The idea is they first compare similarity between any two visual words, and then they cluster the most similar visual word together first, and then they do this cluster, repeat this clustering process again and again until all visual words are clustered to only one group. Okay, so based on the process of the clustering, we can construct a tree like this. And based on this tree, we can know that visual world V1 and V2 are very similar. Visual world V3 and V4 are very similar. And on the other hand, visual world V3 and V6 are not so similar, but in contrast to V1 and V2, V3 is more similar to V6. Okay, so we can construct a visual ontology like this. And based on this tree, they use JCN to estimate the visual relatedness. And the JCN idea was proposed in also by the same research group. They proposed this method in year 2008 in SIGIR conference. The idea is that this, based on this tree, they try to find the information content first. Okay, so the distance between visual world Vi and the visual world Vj is defined like this. We first measure the information content of each visual word, and then we subtract the summation of these two values by the information content of the local common ancestor of Vi and Vj. Okay, and this is defined as the distance between Vi and Vj. Okay, so how can we calculate the information content? The idea is quite simple. It's based on the information theory. We just take the log of the probability of visual world Vi and then take the negative of this value. This is the information content. The idea of information content is that if the probability of a visual world is small, and if it really happens, then the information content would be large. Okay, and this idea is based on information theory. Okay, so now here we can measure, for example, Vi is V1 and V6 is Vj, and now we can calculate the information content of V1, information content of V6, and then the lowest common ancestor between V1 and V6 is actually the node A. So we also calculate the node, the information content of the node A. Okay, and if these two, for example, V1 and V6 are quite different to each other, then the distance between them would be large, because right here this value plus this value, and the lowest common ancestor information content of the lowest common ancestor A will be quite small. Therefore, the distance between V1 and V6 will be quite large. On the other hand, if we measure the distance between V1 and V2, then the local common ancestor is node D, and the information content of node D will be large. Because the probability of the node D is small relative to node A. Therefore, the distance between V1 and V2 will be small. And this is how they measure the visual relatedness. Okay. And on the other hand, the JCN is defined as the similarity between Vi and Vj. So we just take the inverse of the distance. Therefore, we take the distance as the denominator. Okay, and then we can measure the similarity between Vi and Vj. And this calculation can be simplified as this value. So finally, we combine all the factors together. We consider back visual world, we consider motion, we consider relative motion, and now we expand with the visual relatedness. Therefore, for some relative motion and the visual world A and B, the value is calculated by, first we have the relative motion histogram between visual world A and B. And then we consider SA and SB that are visually related to word A and B. So how can we get SA and SB? We just obtain SA and SB based on the visual ontology. Okay, and then we also consider the relative motion between SA and SB, and weighted by the JCN, the similarity between SA and A, the similarity between SB and B, and then we sum them together to do the expansion. So this is the final version of the expanded RMHBOW, or ERMHBOW in short. Therefore, based on the three-dimensional data structure, not only for each visual word, we also consider other visual words that are visually related to the considered visual word A and B. And then we can expand the value. We can expand the value by weighting the visually related visual word. So we have gone through all the process. So let's go back to see the whole framework. So at first, we extract feature point from video frame, and then we construct big of visual word. And by considering the relative motion, we can construct the relative motion histogram of big of visual word. And based on the extracted visual word, we can automatically construct the visual ontology. And based on visual ontology, we can measure the visual relatedness between different visual words. And by considering the visual relatedness, we can expand the relative motion histogram. Okay, so by considering the visual relatedness, we can expand the relative motion histogram of big of visual word, and then finally we get the ERMHBOW. The description above are all for describing a video frame or describe an image. But right now we need to process video event detection, so we need to describe a video rather than just one video frame. So given a video clip, the ERMHBOW is calculated between every two neighboring sample frames. Because we need to consider motion information, therefore we need to jointly calculate the motion information between neighboring video frames. Okay, so for every two neighboring video frame, we can calculate an ERMHBOW for every two. Okay, and the video clip is then represented as a sequence of ERMHBOW. Therefore, for this video, we can represent this video by ERMHBOW1 and then ERMHBOW2 and so on. So we can use a sequence of vectors to represent this video clip. And then, because the target of this paper is to do video event detection, we need to compare the similarity between different video clips. So how can we measure how do we measure the distance between video clips, especially when the length of different video clips may be different? Okay, so right now we represent each video clip by a sequence of vectors. How can we measure the distance between them? One way to do this is adopt the Earth mover distance. Okay, the Earth mover distance was proposed many years ago, but it is used for measuring the distance between video in this paper, published in year 2007 in CVPR. And we can also see this very famous professor Professor Shifu Chang from Columbia University. Okay, and basically, Earth mover distance is a way to measure two sequences of different length. Okay, so you can see that you can think the idea is that they try to find the best match between two sequences. Okay, so they will find a best match between them, and for each of the pair, they measure the distance between Euclidean distance. Okay, so the basic component is the Euclidean distance between ERM HBOW, but they have to find the best match. For example, this one should match to this one. This one should match to this one. This one match to this one. This one match to this one, and so on. And finally, we accumulate, or we take the average of all matches and estimate the Euclidean, the Earth mover distance between them. And if you are interested in the detail, please refer to this paper. So right now, we can measure the distance between any two video clips. Okay. Then how can we determine whether two videos corresponding to the same video event? Okay. So we use an SVM to do classification. The EMD distance between video clips is incorporated into the kernel function of the SVM framework by using the Gaussian function. So we can see that we have a video, we have another video, and we calculate the EMD between them. And then we put this EMD value into an SVM classifier. And then this SVM classifier will tell us whether these two videos corresponding to the same video event or not. Okay, so we train an SVM classifier based on the EMD between different pairs of video clips, and then we can take the positive samples from the EMDs calculated based on the videos corresponding to the same video event, and we can get the negative samples based on the EMD calculated from the video corresponding to different video frames. Therefore, we can construct a classifier to do video event detection. Now the experiment, they evaluate performance based on the Traffic 2005 development data, and they pick 14 events like existing car, handshaking, running, demonstration, protest, walking, riot, people marching, dancing, greeting, shooting, airplane flying, street battle, people crying and singing. They pick these 14 events for evaluation. And this is the performance comparison. This is the performance obtained by different methods. The y-axis is the 14 video events, and the x-axis is the average precision. Here we can see the keyframe best method is the static backward visual word, or the key or the expansion backward visual word, and the sequence-based approach is the relative motion histogram, relative motion histogram, okay, and the expanding motion histogram. So they evaluate various settings, and from here we can see that overall the ERM HBOW, that means if they jointly consider backward visual word, relative position, and visual relatedness, they achieve the best performance, like street battle, airplane flying, people marching, walking, and running, and many of them. they perform the best. Okay, so this figure verify the effectiveness of jointly considered visual word and layer motion, especially layer relative motion. And this table show detailed result of the performance based on different parameter settings. We show MAP. We just check the MAP, mean average precision. If we just use the big visual word, we got 20%. If we just use the Gaussian, if we just use the motion histogram, we got around 15%. If we use the ERM HBOW, we got almost 26% accuracy. So by comparing the ERM HBOW versus the motion distribution, we improve around 74%. And if we compare the ERM HBOW with the conventional BOW, we improve around 24%. Okay, so this is another illustration showing the performance difference. Okay, so basically the ERM HBOW achieved the best, and we can see that it significantly boosts the performance from around 15% to 26%. And these are some sample results. Okay, if we want to detect demonstration port text, if we just rely on big visual word, that is, if we just describe the what aspect, then the top 5 result, from the top 5 result, the top 3 are wrong. If we just rely on motion histogram, that is, if we just describe how object move, then from the top 5 result, the top 4 are wrong. If we jointly consider both of them, from the only one of the top 5 result is wrong. So in conclusion, sequencing is necessary for event detection, and the motion of big visual word is good for event description. Especially relative motion can be used to boost the performance. And then by considering the visual relatedness to do visual word disambiguation is useful. Okay, and of course we can improve the speed to do feature extraction, and we can devise more compact feature representation to get better performance. And about the application of local feature point and the original SIFT descriptor, we can refer to the following literature. So this paper is the canonical, is the most typical, most important paper to describe the SIFT descriptor. And right here, we have already introduced this paper published in ACM Multimedia, year 2008. And you can refer to semantic relationship from this paper and earth mover distance from this paper.